Hi! Today we're going to talk a little bit about how we can use R on a cluster. Now a cluster here is a connection of a bunch of computers all together, which means that we sort of have the ability to run our job not just on one computer, which is what we're doing locally, but we can run our job or our computation across multiple computers and get the results back faster. Generally, when we have a cluster, we normally have our own computer down below, right over here. We log into what's known as a login node or a head node, and from that login and head node, we sort of go across into a scheduling system that will take our computation and take our job and distribute it out over into a compute node. And that compute node is what is actually going to crunch all of our data for us. Now, cluster systems also are known for being able to work with large amounts of data, and to do that, you usually have some kind of shared storage that's connected across the system. The example that I'm going to use in terms of the cluster today is basically FarmShare. FarmShare is a community computing environment at Stanford. You can use this for just about anything up until you start getting into high-risk kind of data analyses with personally identifiable information. So it's a great learning cluster is what I would say if you're at Stanford. With that in mind, what we're sort of looking for on this FarmShare cluster is a way that we can take our user device, we can connect into these head nodes, rice, and then from rice we can go into one of the compute clusters that sort of exists, iron, rye, wheat, or oat, and then access data that might be held inside of the Stanford AFS system. To do that, we're going to sort of use the future R package, and we're going to set up things with respect to what's known as a future topology, where what we're doing here is we're saying there are 3 steps in order to run our code. The first step is we need to log in. The next step is we need to run a job scheduler. And then the last, or the third step here, is to sort of allow us to do parallelization, or having our work done simultaneously on that same computer, that compute node that we had, through a multi-session approach. So this will break down into sort of this topology and execution hierarchy that we see here, where on the left-hand side, right, we have the 3 different stages or levels to our future plan. You can see the first one is just logging in directly from R, going on to the login node. From the login node, going across into our second level for the future, which is actually sending our work out onto the compute nodes through the Slurm scheduler. And then down one more below, that's when we start to say we want parallelization on the compute node that has been allocated to us. So let's go and take a brief look at what this looks like inside of R. So here what I'm going to very quickly do is I'm going to gently load in a few packages, and I'm going to now initiate a conversation with the FarmShare cluster by using plan login. Now, once we are logged on to the cluster, the next step that we need to do is we need to specify the resources and indicate to the scheduler, which handles how work is distributed across the compute nodes, what kinds of requirements that we have in order to run our computations successfully. To do that, what we're going to do is we're going to use the BatchTools package. There's already an existing future extension that allows us to use BatchTools. And then what we're going to say here is a series of statements regarding resources. So here we're saying we want 2 cores. We want to queue this in the normal queue. Now each sort of compute node on a cluster, it can belong to different kinds of queues. Like you could have one that's specifically for GPUs. You could have one that's specifically for a given research group or PI. So you do want to make sure that you correctly specify your queue. And then last but not least, we have first the wall time, which tells us how long our job is going to be running for. So if you have a stopwatch and then you start the stopwatch, right at 1 minute, it's going to make everything stop, regardless of whether or not it's done. This is really great protection if you have here, for some reason, code that might not immediately converge, or if you just have an errant script that you forget to sort of exit out of once the calculation is done. And then next we have here the memory, or how much RAM that we sort of need in order for the data to be brought in, or for one of our computations to take place inside of, let's say, a really dense matrix. So with that being said, let's go ahead and configure Slurm with our resource tweaks. And then what we're going to do is we're actually going to create a series of the topologies using those three components, or two components that we discussed, and then we're going to add in one additional component called multi-session, where multi-session allows us to have parallelization across different cores. Core here would be like a central processing unit, or your CPU. You know, normally have like a quad core, so you have 4 cores that are present. And in our case, when we specified for BatchTools Slurm, we said we wanted 2 CPUs. So basically, we're going to split the work on that single compute node across 2 different CPUs. So if we go down, we're now sort of at this nested future topology, where what we're going to do for the first part is we're going to just make sure that when we launch this job, we are launching it definitely on the cluster, so we're going to get the login node information. Then what we're going to do is we're going to send 4 different jobs out, which means we'll have 4 unique job identifiers in Slurm. Each of these basically has its own compute node that will be allocated for it. And then for the third nesting, what we have here is basically the parallelization on that compute node. And we're using here a bunch of system properties to just emphasize and to show you that this is really actually running on a cluster system. It's running through a scheduler. It's amazing, is what I will say. So on that end, what we're really quickly going to do is I'm going to log in under my terminal real quick onto FarmShare. So I'm going to say SSH FarmShare, and you're going to see it takes a little bit of time to get into the FarmShare system for me. But once I'm there, what I'm going to do is I'm going to sort of first show you that, again, nothing in terms of the scheduler jobs are actively running. I'm going to do that by using sq-u, and then I'm going to specify here a generic username, which is reading off of an environment variable, and it's going to fill in my own details. So we can see here I have no jobs running. I just have here a table that emphasizes, we have no jobs running. So I'm going to jump back now over into R, and I'm going to run that first topology. And what's going to happen here is it's running. If I jump back and I say SQ, we can see the first job was triggered, and it's been distributed out to week 1, right? And we can see 2 other jobs coming online. Now we're at 4 jobs, and now we're at 0 jobs, which means all of our jobs have successfully completed. So if I go back over into R and I go ahead and I show you the results, I'm going to just do print X. Notice that we've connected onto the cluster and we've logged into the RICE1 login node. On the compute side, we've been distributed over to the wheat1 computer in the compute node cluster. And then you can see on the wheat1 host, we've been given different processor IDs. So our session has effectively been parallelized. Now, what we can do real quick is we can save these results into like a CSV. So again, we've downloaded data, or we've gotten data from the cluster, we've brought it locally, and now we can sort of save it. All through, again, these future topologies. Once we're done, we're going to reset everything. So we'll say plan sequential, and lo and behold, everything is done. Now, I want to do one more quick example with you while I have you. And I want to show, again, that we can sort of create a local data set and we can port it over into FarmShare. So, or our cluster directly from R. Right? We don't have to use an FTP client. We don't have to use SCP or rsync, which are file transfer protocols from the command line. Instead, we can do this directly inside of R using Future. Now, I do want to emphasize it's generally better practice not to do this because, again, if you have larger data files, this sort of will gently start to break in terms of the serialization because, again, this isn't necessarily meant for data transfer. It's meant more for handling, setting up computations, and getting aggregate results back into your local R session. So with that disclaimer out of the way, again, we're going to really quickly log back in to the cluster. And what I'm going to do when I log back into the cluster is I'm going to set up locally a series of data. So here we're going to say, we have a local data frame that's been randomly generated, and you can see over here X, Y. Okay. Now, because we've logged into the cluster and we just have one plan topology, what we're going to do next is we're just going to say X is going to be equivalent to this write statement, and what will happen is we should, on the cluster, get this data-on-cluster.csv written out. So if we go ahead and we run this line of code real quick, right, and I just say X, you can see that I have null here, right, so write CSV isn't returning a status. If I run another command, in that case list.files, which means that I'll get an entire list of every file in the directory, and I'll be saved into Y. You can see very quickly here, right, we have our data on the cluster.csv, which means that we've taken the data set that's in our local R memory and we've ported it over to the cluster and we've written it onto the cluster's file system. Again, let me say that one more time. What we've done here is we've created or imported data into our local environment. Through a future topology that's logging in to a head node, we've then have transferred that local data through variable sharing onto the cluster. We've written it as a data file inside of the cluster that you can see right over here. So let's now go in the reverse direction. And in the reverse direction, what we want to do is we want to see if we can read the data that's on the cluster and then send the data back over to us. So here we've created a way of reading the data into my data, and we're saving sort of the results into Z. And lo and behold, right, not only do we get the print statement, but we also get here the actual value for my data. So this is really sort of powerful. Again, Z actually is a full-fledged data frame, and you also now have a print trace, or the entire print summary also attached to Z. So this is very exciting, is what I would say. Now, to get this all done, we did have to make a few tweaks onto our cluster. The first thing that we had to do was we had to install some R packages onto the cluster. One of those R packages is Future. The other R package that we needed was future.batchtools, and that brought in a few dependencies that were already set up for us. Once we had those R packages present, the next thing that we did is we created here a template file that sits in our local home directory. So / is where this is going to sit. And basically what's happening in this template that we have is we're gently setting different properties that we were specifying in our resources key. So here we're saying resources queue, resources wall time, resources and CPU, and then resources memory. We can add additional ones automatically if we wanted to, but I've generally preferred to make sure that everything is more specified to avoid any issues with minus signs or underscores and things like that. And then over here, what we're doing here is if we don't specify a partition, we just leave this variable blank. But if we do specify a partition, so which group the compute nodes should belong to, we add that in. And then next, on a cluster system, one of the huge differences here is it's a shared compute environment, which means that we have a bunch of different software packages that are all present. So we have to specifically load in software that we want to use. So here we're loading in the version of R for 4.40. I think also in this cluster system, there's like 4.33 that's present. If we go down one more, right, we can now also sort of set here or store variables like whether or not we want debugging enabled and other things like that. And then lastly, down below here, we have the batch tools job collection where this is sort of what allows a lot of the results to be collated together and then sent back through the future topology. So this was the sort of second part, which again, this is sort of structuring how the job should be sent to the Slurm scheduler. And then the last part that we have over here is in our bash RC file, what's happening is we're sort of loading in R when we connect into the cluster. So we're always making sure that the module R file is available. And we need this because if the remote login node doesn't have R and it doesn't have future or batch tools installed, then it can't actually do this topologies approach. So to that end, you usually don't need these first two statements over here, but for whatever reason, on FarmShare itself, which is the cluster that we've been working with, they are required, and basically they're allowing you to use modular files. Usually you can get by just with this one statement where you're saying command-v and then you're checking to see if there's actually any output, and if there is, then you can go ahead and load in your modules. So overall, again, this is really powerful. You just saw that we were able to do compute directly from our local R session with a remote cluster, and we could bring the results back in, or we could send data out. Thank you guys so much for watching. I hope to see you in the next video. Bye now.